Hey guys, so in this video, we're going to cover moving charges in magnetic fields. Okay, so we're going to look at what happens and then some applications. So think about cyclotrons and mass spectrometers. Cyclotrons and mass spectrometers aren't mentioned in a lot of specifications, but again, it could be an application question and it is quite a common application question. So we're going to go over it. So moving charge magnetic field. Okay, so first thing we know is we know that F equals BIL. We know that from our GCSEs. Force equals magnetic flux density times our current times our length. And I can say that's also equal to BQV. And the reason why is because we know Q is equal to IT, charge is equal to current times time. So current is equal to charge divided by time. So what I can write now, instead of writing BIL, I can write B times Q over T times by length. And I know speed is equal to distance divided by time. So if I have a length divided by time, I know it's the speed. So that's why that can be written as BQV. So I just write little q instead of a capital Q, because normally when we look at moving charge magnetic field, we're looking at the charge of a proton or charge of an electron, a single proton or a single electron. So that's why I represent it with Q. Okay, so let's say we have a magnetic field. So we use X's to represent our magnetic field. So X's always show us that the magnetic field is acting into the board. Okay, or into your page. And let's say I have some positive charge here. So let's say we've got our positive charge here. Maybe it's a proton. Okay, my proton is initially moving in this direction. The only reason we're going to get a force is because we need the magnetic field. So we need the magnetic field always to be perpendicular to the speed or the velocity of that particle. If that happens, we're then going to get a force that is also perpendicular. So that's just a quick way of writing perpendicular. So if you use Fleming's left-hand rule, and what you're going to have, we know Fleming's left-hand rule is our thumb shows us force, our first finger shows us B, our magnetic field strength, and our second finger shows us the current. So what I have is my magnetic field is going into my page or into the board. I have my particle moving towards the right, so there's going to be a force on it trying to push it up. So there's a force on it trying to push it up. So what happens then is that particle starts to move in a circular motion. And when the particle starts moving in circular motion, what we can say now is we can use our circular motion equations. So instead of write F equals ma, what we can write is m v squared over r, or m w squared times by r. So v is our linear velocity and w is our angular velocity. So again, v is your linear velocity and w is your angular velocity. So hopefully what I can see before is when we can write force, we can write it as F is BQV. Because there's a velocity in there, I'm going to use this part of the equation. So what I can say now is BQV is equal to mv squared over r. Hopefully you can see my two velocities are going to cancel. So I want to write what radius is. I can see it's mass times velocity divided by b times by q. So that's how we can figure out the radius of the path of our particle, in this case our proton, if it's got inside a magnetic field with its velocity perpendicular to the direction of its magnetic field. Okay, so just change question. One of the applications could be a cyclotron. So what a cyclotron is you might have seen it referred to as the Ds. So we have our two Ds. They're called Ds just because they look like Ds. And our two Ds are inside a magnetic field, right? So let's say we have a magnetic field this time that's going out of the page, right? So that magnetic field is going out of the page is applied across the whole cyclotron. In cyclotrons, you might have seen before, what we use them to accelerate particles. Okay, so they're just like massive circles. Normally they're underground, and we just use them to accelerate particles. So let's say we got a source of our protons. And what's going to happen is we're going to apply an alternating potential difference across the two Ds. So let's say this D is negative and this D is positive. What's going to happen is my positive proton is going to get accelerated across the gap towards that negative D. And then when it's inside the D, what happens is that it's going to be moving perpendicular to the magnetic field. So what's going to happen is we're going to get a force on it. So there's the direction of my velocity, and we said our magnetic field this time is coming out. So if my magnetic field now is coming out, and that's the direction of my velocity, we know there's going to be a force on it, and again, keeping it in a circular motion. When it gets to this point, what happens is this alternating potential difference, it switches. And it switches so that now this side becomes negative and that side becomes positive. So it switches to switch the potential difference of the Ds. So what's happening now is my positive proton will get accelerated across the gap towards that negative D. When it's inside the D, that because its velocity is perpendicular to the magnetic field, it moves in a circular motion. Then it gets accelerated across the D, because again, what happens is we switch the poles, we switch the potential difference. Now that's negative and that's positive, and again, it moves in a circular path. And the reason we can see that its radius increasing is because we know energy is equal to potential difference times by charge. So every time I try to move my one proton across that potential difference, it's gaining energy. So it's increasing energy. And I know it's increasing kinetic energy. And kinetic energy, or EK, is 1/2 of mv squared. So every time I increase its energy, I increase its speed. And we can see here, if we increase the speed, increases value of v, what happens is the radius is going to increase. So that's why the radius of the path keeps increasing, and it's going to keep getting accelerated across, and the radius of the path keeps getting accelerating until eventually we've reached the radius that it's going to emerge from our cyclotron. Right, so the whole point was we want to keep speeding up this proton. What's good about it is even though the radius keeps increasing, we can keep the frequency that this alternating potential difference changes the same. And the reason we keep it the same is because we know the equation speed is equal to distance divided by time. So if I want to do the speed or the velocity of my proton, let's say it goes for a full circle. A full circle is 2 pi r, and it goes for that in the full capital T for full time period. What we can do now is we can equate this equation to this equation. So I want to rearrange this equation. I can write speed is equal to r b times q over m. So what I can write is bq times by r is equal to mv. So v is r bq over m. So now I can equate that to r bq over m. And hopefully you can see is my two radiuses will cancel now. So what I have now is 2 pi over the time period is equal to the magnetic field strength times the charge divided by its mass. So when I write an equation for what time period is, the time of one full circle, what I can write now is it's going to equal 2 pi times by m divided by b times by q. Okay, so that's what we're saying is our time period. Remember, time period is always equal to 1 over the frequency. Okay, so time period is equal to 1 over frequency. So to write the frequency, what I can say then is it's bq over 2 pi m. So bq over 2 pi m. And that's if we did a full circle, but what it's actually doing, it's not doing a full circle, it's only doing half a circle. So the frequency it's going to switch frequencies every half circle. So that's why the frequency is number of, remember, time period is number of full cycles it completes. So the full cycle completes is this, but the frequency in 1D would just be half of this. Okay, another place you might see it is that you might look at a mass spectrometer. So if we change to green for a mass spectrometer. So mass spectrometers you might see in chemistry. So mass spectrometers, what they are is we have this thing called a velocity selector. So a velocity selector is when we both have a magnetic field and an electric field. So what I have here is I have an electric field between my two plates. So we know an electric field strength is force per unit positive test charge. And I have a magnetic field because I have a magnetic field applied across it. So what happens is we ionize all the particles, and we have our particles, let's say they're all positive, coming into this velocity selector. And what you might see this coming up with the question is, how come they're all going to merge with the same speed? And the reason they merge with the same speed is because they both experience an electric field and a magnetic field. Remember, the magnetic field, the force, is equal to BQV. So what I can say is that each particle, each proton is going to have two forces on it. It's going to have the force due to the electric field, and it's going to have a force due to the magnetic field. And they're going to be exactly equal. If I want that particle to emerge, it's a straight line. So what we can see now is you cancel the charge both times, and I can see the speed that it comes out with is going to be the electric field divided by the magnetic field. Another way to write electric field for a parallel plate capacitor, we know is V over D times the magnetic field strength. So whatever the potential difference is between my plates divided by the distance between them divided by the magnetic field is the velocity they come out with. Once they all come out the same velocity, then we put them inside just a magnetic field. And when we put them inside a magnetic field, we put the magnetic field perpendicular to its velocity. And what's going to happen then is our particle is going to start moving in a circular motion. And again, what we can say is because it's moving in a circular motion, we can say that the only thing that's in here now is magnetic field. So we know that F is equal to BQV, and that's equal to our mv squared over r. So when we rearrange this like we did over here, what we come out with is that our radius is equal to mv over b times q. And we just said they're going to come out with all the same velocity because they were determined in that velocity selector. And the B is the magnetic field. That's another constant because it's applied across the whole mass spectrometer. So what we can see is the radius then is going to be proportional to mass per unit charge, or the radius is going to be proportional to the specific charge. So that's how we can use mass spectrometers to find out what the specific charge is of the different elements they hit detector, because we can see what's the different heights that they hit that detector at. So hopefully you find this video useful, and if you did, remember to sign up to our online classes at the myadspace.co.uk website.